Hello, everyone. Thank you for joining us today. I'm Laura, and I'm the editor of PIC magazine. I'm delighted to introduce VPI Photonics, who will be presenting the latest updates to their design and simulation services, specifically this time for modeling and optimizing PICs for data center interconnects. Chris, would you like to begin?
Yeah, thanks, Laura. Yeah, thanks everybody for joining us today. I'm Chris Maloney. I'm the Managing Director of U.S. Operations at VPI Photonics. And today I'm joined by our technical experts, Eugene Sokolov, who is a Principal Application Engineer for our Photonic Circuit software, and Nabras Deeb, who's an Optical Systems Application Specialist. So as you've most likely heard in the news or are already aware of, data center traffic is growing rapidly due to things like AI and machine learning, cloud computing, video streaming, gaming, Internet of Things, among other digital transformations. So, and to try to quantify this impact of traffic, McKinsey's actually released some projections of global data center power demands. And just to interpret this plot here, in the lower left corner of each of the blue squares is this dashed square showing the demand, the power demand in 2023. So 55 gigawatts of power, and each of the larger squares represents a low, mid, and upper range scenarios for the projected power demands by 2030. So this ranges from anywhere from 3 times to almost 6 times the demand seen in 2023. So this is really driving the demand for more efficient data centers and therefore more efficient interconnect solutions within the data center, which is what we'll be talking about more today. So let's look a little bit closer at how connections are actually made within the data center networks. So first, data center campuses all need to be connected to each other. So this could be connecting regional data centers together globally, spanning anywhere from hundreds to thousands of kilometers. And data centers within those campuses also need to be connected to each other, which could just be a few kilometers. And then even inside the data center, you have spine and leaf switches, which need to be connected. And then the servers within the racks even need to be linked. And so each link within this full data center network, they have different requirements for link length, performance, and cost. And therefore, each link requires a unique solution. So for some of the longer reach applications, coherent optical interconnects are used. And coherent solutions use higher order modulation formats, transmitting information using both phase and amplitude properties of light, allowing you to send multiple bits per symbol. That together with solutions like wavelength division multiplexing results in very high spectral efficiency. But these links are also more complicated and they require DSP and are therefore more expensive. So intensity modulated direct detector, IMDD systems, offer a more simple, more cost-effective solution that are ideal for more short or moderate reach situations, often used to connect data centers together or for intra-data center links. And it's still possible to send multiple bits per symbol with this approach, but in this case, we're just modulating the intensity. And there's a whole discussion going on right now of whether or not these coherent solutions will actually enter the data center as data rates continue to increase and data centers evolve. And then lastly, copper interconnects are currently being used for very short reach links, as they're the most simple and lowest cost solution. But as data rates increase, their reach actually becomes more limited, and they will require more power to attain that same reach. So as electrical interconnects start to hit their limits, they're being replaced by optical interconnects to improve data center efficiency and also scalability. So optical interconnects are already being used for data center network scale out. So to connect data centers together, as well as connecting server racks and switches together, because of their higher bandwidth and longer reach properties. Now, photonic integrated circuits, or PICs, are used to enhance the capabilities of optical interconnects. They're already being used in pluggable transceivers, So for example, you might think of an EML, which is a DFB laser and an electroabsorption modulator all together on a single indium phosphide chip. They're also being used in higher performance co-packaged optic solutions where the photonic chip is packaged directly on the switch PCB to be placed closer to the processing units. And compared to discrete components, PICs are more energy efficient and provide higher bandwidth density, all leading to a lower cost per bit. So therefore, PIC-based optical interconnects are replacing copper links to overcome the reach limitations in copper at those higher data rates. So PICs actually enable data center scale up, so connecting multiple processing units together within a server, which is crucial, especially for applications like AI model training, where a large number of GPUs are needed to be used in parallel together. And many companies are already working in this area. You can see one example that does a good job of illustrating their concept is Intel's OCI chiplet, where you can see the PIC mounted directly onto the electrical IC right next to the processing unit. And so I believe we're at an inflection point right now. PICs are shaping the future of data centers, enabling faster, more scalable, and energy efficient architectures. So integrating PICs into optical interconnects is a great solution, but it comes with its own set of challenges, especially when talking about the design complexity. So for example, you might have a PIC designer. Today that will be Eugene, who's working on designing and modeling a silicon photonics microring modulator, which is not a trivial task in itself. And when he's done, he will pass that model to Nebraska, who will represent the optical systems team, to integrate it into the full optical interconnect system, which may contain electrical and optical components in the transmitter and in the receiver. It might contain a fiber span, multiplexing, equalization, DSP, and more. So also not a trivial task. And so those two teams need to work together to do some file exchange to ensure that the PIC model can be used in the full system simulation. Also, this microring modulator may degrade the performance of the system in some unexpected way. So the teams actually need to go back and forth between the system simulation and the photonic circuit design, which can be complicated and time-consuming. So what we provide is a solution that brings together PIC design and system simulation, all within VPI Photonics design suite. So it's a single user interface and single design environment. And we've integrated the system solutions together so that your PIC can be tuned and optimized while considering the full system level performance. So schematics can simply be shared between the PIC designer and the optical systems team, so they can collaborate together, saving time, but also reaching the optimized PIC performance that considers the full optical interconnect system. So today we'll be walking through a few tutorials actually demonstrating this workflow. To give you a little background about VPI Photonics, if you're not familiar, we've been providing photonic design automation software for over 25 years. And we provide tools ranging from device simulation of waveguides and fibers to component design for PICs, up to transmission design for full optical interconnect systems, and even for link engineering to help lay out and optimize a full fiber network. Today, we are going to be focused on VPI Photonics Design Suite, specifically using the two solutions, VPI Transmission Maker Optical Systems, together with VPI Component Maker Photonic Circuits. But you should be aware of our other software tools. We've developed them all in-house so they can all be integrated together in a complete photonic design workflow. And if you check out our YouTube channel, you can see a number of tutorials going through many of these different tools. To share more details specifically about VPI Transmission Maker Optical Systems, it can be used for a wide range of applications. So today we're going to be focusing on short reach optical interconnects, but it also supports ultra long haul DWDM systems, even radio over fiber and laser SATCOM simulations. It can be used to simulate single mode and multi-mode fibers, explore different coding and modulation formats, study different DSP algorithms, compensation strategies, and equalization strategies as well. It also provides very flexible analysis tools to generate eye and constellation diagrams, and also to evaluate different metrics like bit error rate, TDEC-Q, OMA, extinction ratio, and more. We'll also be focusing today on VPI component maker photonic circuits, which supports more physical and bidirectional modeling on a smaller length scale and time scale for active components, for signal processing elements, and for passive circuits. Now, this tool is material agnostic, so simulations for hybrid PICs are supported. And this solution enables you to design your PIC, look at different design alternatives for it, study fabrication tolerances, and in the end, tune and optimize your circuit parameters. And one of the highlights of this tool is our active component model, the Photonics transmission line laser model. In this is an example at the bottom. It's a widely tunable hybrid 3.5 silicon laser. You can see that this photonic TLM model is used to model the SOA between the two ring mirrors. And so it can account for impairments like back reflections, two-photon absorption, carrier dynamics, current nonlinearities like four-wave mixing, and more. But we also support Foundry PDKs with the software, and then actually provide a framework for you to customize your own PDK from your own measurements or simulations. And you can encrypt those models, you can share them with other teams or with your customers to ensure your IP stays protected. So let's take a look at today's agenda. We've just wrapped up the background and motivation section. Next, we'll be going through two examples. The first starts from the optical system engineer's perspective when upgrading an existing system to an 800G PAM4 DWDM system. And it will be integrating silicon photonic microring modulators as well as ring resonators that have already been modeled, but now will require some tuning and optimization for this optimal system performance. The second will focus more on the PIC modeling side of things of an IQ modulator based on thin film lithium niobate, a 90-degree hybrid based on a MMI device, and integrating those models into a 32-QAM coherent system. And with whatever time we have left, we'll wrap up with an audience Q&A, so stick around for that. Make sure you put your questions in the question box in the chat. And with that, I'd like to turn things over to Nebraska.
Okay, thank you, Chris. Okay, so this is the user interface for VPI Photonics Design Suite, and I have here the first schematic that's based on IMDD. I have activated both the tool for optical systems and photonic circuits because this schematic uses both like components from the libraries of both products, optical systems and photonic circuits. Now, the system here is based on PAM4, which has a huge interest in data center applications. The transmission distance for this system is up to 2 kilometers, which is also which can be used in many data center applications. This is a DWDM system initially with 4 channels and with a symbol rate of 53 gigabaud. So this supports 100 gigabit per second per channel. So initially it's 400G, but we will be looking at the scenario of upgrading this to 800G. Now, the concept of the system is not new, as we see in this figure, and which is taken from reference 1 here. That's from 2006. So the concept is having a WDM source here, as you see, and then modulating the output using a set of cascaded ring modulators. And then at the receiver side, then we demultiplex these channels using a set of ring resonator filters. So then we do detection. So although this is not new, but the interest in ring modulators and ring filters continues to increase, especially for data center applications. There is tons of literature on this in this field. You can see newer papers here. As you see, we have papers references 2 and 3 just as examples, but there is a lot out there on these components for data center applications. Now let's look at the schematic itself. You see here to implement this concept, we have here at the transmitter side, we have the laser sources, and we construct an array of these. So you see these modules here, the red modules. These modules help to replicate so to duplicate a module. For example, here using this module, source GR or source graphical, helps me to create an array of lasers, whereas this next one, chain GR, helps me to create an array of modulators in a cascaded manner, or like a chain. The last module here is similar but different. So it also helps me to create an array of receivers, but in a parallel manner. So the receivers here are set or created as in parallel. Okay, so let's go back here. So then using this multiplexer, we multiplex these tones coming out from this array of lasers. Then we have the like a comp signal here at the output of the multiplexer. Now these modulators, initially we have 4 modulators for the 4 channels, and then each modulator, they are cascaded again. So each modulator is tuned to a specific wavelength, ideally, so that it applies the modulation to that specific wavelength. There will be some leakage to other channels that we'll be looking at. But then at the output here, we have the modulated signal, the DWDM modulated signal, with a channel spacing of 200 gigahertz. We do the transmission through the fiber here, and by the way, this is done in the O band, so all the channels. The different effects of fiber are accounted for, such as chromatic dispersion, attenuation, nonlinearities. And then after transmission, we have the filter. So this filter here works as a demultiplexer, and this is based on ring resonator filter. We can look inside, and we see. So these modules are from the library of photonic components in the software, and they give me multiple outputs. So in this case, we have 4 outputs for the 4 channels, and then they are tuned properly so that they tune to these channels, to these wavelengths. And then at the output here, we detect the signal. So after photo detection for each channel, we do some signal scaling, bandwidth limitation, and feed-forward equalization. And then we assess the TDEC-Q and SER using these modules. Let me run the schematic while we continue explaining it. So again, here, yes, we have 1 receiver, but just a reminder, it's duplicated. So we have 4 of these in parallel. We have signal analyzers here, so we'll be visualizing the signal at the output of the laser source, the WDM source, and at the output of modulators. So that's after modulation, and we're looking at the SER. So that's using this analyzer here. And we'll be looking also at the electrical signal here at this point after equalization. We chose to show the electrical signal for the monitored channel, which chose to be the last channel. So in this case, monitored channel equals number of channels. So this is channel number 4. I already got the results, so it took only 32 seconds to simulate, and we can see the results here. So this is the OSA, or the optical spectrum analyzer. So I see the optical spectrum for the signal. This is at the output of the WDM source. I have the 4 tones with 200 gigahertz channel spacing. Then this is at the transmitter output, as you see, the modulated signals. And here I show this is visualizing the electrical signal here after equalization for channel number 4, as I mentioned. And this is the Q in dB for this channel. We see a good eye opening. And then this is the SER versus channel index. So now this is for 4 channels. So actually here the system works for 400G. And let's say we want to upgrade to 800G. So we have this macro. If we fit this, so we have this macro that helps me to do this. I'm going to run the macro and run for 8 channels. So I can specify the number of channels using this macro. And what this macro does is to update the ring resonator filters here, this galaxy. And also it will update some schematic parameters. So let's run it. And you see now this is done. So now the filter is updated to accommodate 8 channels. And let's run again now. After this update, some parameters were also updated in the schematic using this macro automatically. So if we run again, we can see then the performance with 8 channels instead of 4. So we want to do the 800G. Okay, so we see the results now for this case of 800G. Now we see we have the 8 channels here for the WDM source. Again, this is the modulated channels. And then this is the eye diagram for the last channel, channel number 8 in this case. And we see that the performance is good for the first 6 channels only, but not good for 7 and 8. So I then wonder about this. Let's just to recall, if I switch back, these are the previous results with 4 channels, and these are the new results with 8 channels. So as a system specialist, I go back and try to investigate this to see what the problem is. Why am I not seeing a good performance for channels 7 and 8? But then I see that I would need to reach out to the team of photonic circuits, in my case, Eugene, so to discuss this problem and seeing why this is happening. And actually, I would like to pass the talk to Eugene to tell us more about this and how we managed to identify the problem and solve it. So Eugene, the floor is yours.
Thank you, Nebras, for setting up the problem. So I would be happy to take a closer look into our PIC-based microring structures in the system. So in general, system-level engineers very frequently underestimate the importance of the detailed PIC modeling, right? They frequently base their simulation on higher-level performance metrics and some datasheet models. And in many cases, this works really well. However, not in the case of the advanced state-of-the-art solutions and emerging technologies. So at the same time, accurate modeling is very important because it can reveal us some impairments or maybe some fabrication variability, which is having a very significant impact on the system performance. And maybe we need some design optimization early in the development. So let us take a look how we address this problem on the example of the Microring modulator. So this is the system we would like to explore, and so the design of silicon Microring modulator is relatively simple, right? So we have a ring resonator coupled to a waveguide, and it resonates on a specific wavelengths. And the position and transmission, it depends on the effective index. And once we start either deplete carriers, usually deplete carriers, or then we start modifying the effective index. And this is how we perform the modulation. So silicon photonics is not a new technology really already, so it is pretty well established, and for many reasons, right? So I'm sure all of us know this, like it is CMOS compatible technology, right? So it allows for compact size, lower power consumption, and as we can see in this particular example, it's really suitable for DWDM applications. However, there are tons of other researches, and just one picture here from this research. They try to do some Z-shape PN junction to optimize the overlap between the PN junction and the waveguide mode. So again, it's not the topic for this conversation today. It's more we're interested how we can adjust the parameters and get back into the system. And for that, we really propose a framework of characterization test benches. So let me open the first one. So this is universal test bench, which works regardless the actual design and model implementation of the Microring modulator. And so it covers a set of different characterization modes. And for this, we either visualize the spectrum, right, and analyze the spectrum of our Microring modulator sitting here in the middle, or we just launch the CW laser, the ideal CW laser, on a particular frequency. And then we have some visualization and analysis tools. So yeah, let's just visualize the transfer function of our Microring modulator. So this is a typical transfer function, right? So we can see it's pretty narrow filter. And now if we start applying the reverse bias to our Microring modulator, right? So I'm using this little sweep routine to automate this process. We can actually see how the performance of the transfer function changes, right? And now if we tune to a particular frequency here, let's say this is our wavelengths of the first channel, and we start varying the reverse bias voltage, we can see that our channel would see different transmission. So this is how we achieve the modulation. So that's the basic operation of the Microring modulator. However, there is also one more feature of the transfer function which we currently do not discuss. So if I zoom out, I can see that my transfer function repeats itself. And this makes a lot of sense if you remember how the Microring modulator operates, right? So it just matching phase conditions. So if our phase differs just 2 pi, we're gonna see the repetition. Let me actually switch to the gigahertz here. And let me add another marker. So now we have measured this distance, which is called free spectral range. And if I measure the distance between two neighboring peaks, I can see that it's a little bit over than 1 gigahertz. So now remember, in Nebraska simulation, we wanted to do 200 gigahertz channel spacing, and we wanted to feed 8 channels. So obviously, we cannot do that, right? We can't do just because our free spectral range is smaller, so it doesn't really fit all of the required channels. So that's a problem, and how can we solve it? So for this, we can actually vary the design parameters of our Microring modulator, and the natural one is actually having tuned the ring radius. So I'm running another test bench here, which varies my ring radius. Oops. And let me switch to the single. So now once we start varying the radius, we can see that our free spectral range changes. And we can see the value of the radius here in the middle. And so the smaller is the radius, the larger is our free speckle range. So in fact, if we measure again the free speckle range, in this case, we will see that having ring radius of 6 micron actually would be able to feed all of our channels. So we're gonna stick with this value. However, there are a couple more things going on, right? So if I show all of the peaks again, we can see that there are two things happening. We also shift our frequencies, our resonance frequencies, right? So if we had them tuned to our channel frequencies, this is not the case once we change the radius. So we need to do the retuning again. And another thing is happening that actually our extinction ratio changes, right? And this has a lot of sense because, we also need to adjust the attenuation. So let's address those two problems. So for this, I go back to my schematic. So first of all, I need to specify the updated value for my Microring modulator. So we specified 6 micron because we found this to be optimum solution to achieve the desired free speckle range. And now we can run this channel tuning test bench. And there are two things happening here. So one, we sweep our channel index to tune, to tune our CW laser to our channel frequency, and then we perform the tuning of the phase shift, right, for each of the channels. And usually this could be happening with some thermal phase shifter. So now if I check the simulation, yeah, we can see that our channels are tuned again. So we can actually see this by the fact that our first channel is tuned to this first channel wavelength. And, we find all of those required phases to achieve this tuning. So what we need to do now, we need to take those values, right, and get them back to the schematic. So here we have the global parameter, channel tuning MRM, right, which goes then into the tuning phase shift of our micromodulator. So yeah, we can also automate this process. So I just run this macro here to update those parameters. So those are exactly the same as we specified, as we obtained in our optimization routine. And the second thing which we wanted to do is actually to achieve this desired extinction ratio, right? So currently it's just minus 14 dB, and that's maybe not as efficient for best performance. And in fact, we need to do this because changing the radius of the ring, we should actually change the attenuation as well. So that's what we are doing in this test bench. We are actually varying attenuation so that we meet the desired target of the extinction ratio of minus 25 dB. So this is the value we found. We can just click the button and transfer this value into our attenuation value of the Microring modulator. There's one final step that usually we don't really operate at this exact location. So usually we want to detune a little bit it from the resonance frequency from the channel frequency. So one last final touch is that we actually need to do this resonance detuning by applying just a small additional phase shift. And yes, we can find it as well. So we pass it to this global parameter. To this global parameter resonance detuning. And so now if I visualize the transfer function, we can see that, yes, we obtained the right tuning and our extinction ratio has the desired value. Okay, that's enough for Microring modulator. We have another structure for Microring-based resonators, and that's again a pretty big topic. In fact, a couple of years ago we did the whole webinar with our partners. So yeah, please explore this webinar. So the structure is relatively simple again. So we have multiple rings stuck together, and so if we choose the coupling between them properly and decide this properly, then we can obtain this kind of a flat top passband filter. Again, fabrication tolerances I plotted here. So we got the same problem, right? So we need to tune those rings to our desired frequencies. So maybe let me just do this little run, but there are other things as well, right? So for example, if we want to change the bandwidth of this filter, it's not like just we change the value, right? We actually need to change the geometrical dimensions of those rings, right? The distance between the rings and etc. So that's something which we also need to deal with. But yeah, that's how the tuning works. Again, we need all those phase shifts to tune to proper frequencies. And again, if we want to change the channel spacing, this means we need to do all the retuning once again. Okay, so the question is now, we did all this tuning, right? So how do we pass the adjustments in our models to the system? And there are a couple of things. So one thing is actually that we support the module library, right? So this means that, for example, this 3-ring filter is actually shared between different schematics. So if I go to my system schematic, I look inside this cascaded structure, and I look inside this guy. This is exactly the same model, right? So if you do any adjustments here, they automatically synchronize. However, there are also some parameters, right? So for example, in my Microring modulator, we still have this 10 microns radius, attenuation is wrong, and all the phase shifts are wrong. So how can we automatically transfer those parameters, right? And for this, we have also a little macro, because it's very easy to forget to transfer something. So we automate this process. So I can just click this macro, and it automatically goes to my test bench and automatically updates all of the values. Okay. Now, what we can do, we can actually try to run the simulation again. Let me run the simulation and see if the fixes we applied actually help to improve the performance of the system. So for that, we can actually check first the results for the case which Nebras was showing for 10 microns. Okay, so Microring modulator, and as you remember, those channels 7 and 8 were particularly bad. And again, this makes sense because of this free spectral range, right? So we remember that once we don't have enough space, they start to interfere with some adjacent channels. And so now we have the results coming up for the updated case. And let's compare if they can really help to improve the performance. Okay, here the results are coming. So here's our updated results. And we can really see the improvement, right? So our eye diagram is now open. We have the improved TDQ, and we can clearly see this in the SCR measurements, right? So if we switch back to the previous case and to the updated, yeah, we can clearly see that we fixed the problems Nebras was showing. Yeah, so this is the end of the first part of the presentation. So we're happy to address your questions once the presentation is over, but now I'm excited to switch gears to the next example of the coherent system. And with that, I give the floor to Chris and Nebras again.
Okay, so now we have discussed the previous example. So the previous example was on IMDD. We had the 800G DWDM system that's based on PAM4. Now, and that was the transmission distance was up to 2 kilometers. Now, I'd like to recall what Chris discussed in the introduction about data center interconnects, that the requirement for transmission distance could be anywhere from tens of meters or hundreds of meters up to tens of kilometers. So it can be anywhere there. So, and here where we see the advantage of coherent technology. So because this allows to achieve higher order modulation formats, which gives me space also to vary the transmission distance. So I can go for a longer transmission distance with a lower order modulation format and so on. And that's very, very convenient or very useful for data center interconnects. So this is, which brings us to the second example here on coherent detection. So we see here the schematic, and again, this is a standard, I'd say, structure for a coherent system, but with some differences. So we see here let's look at the structure of the schematic. We have at the transmitter side, we have the optical frequency comp here. So we generate the tones for the DWDM system, and we have here we do the modulation using the a thin film lithium niobate modulator, and the modulation then is applied to these tones. So the baud rate in this case is 56 gigabaud. We're starting with also we have 8 channels in total for this DWDM system. The channel spacing is 75 gigahertz, and we are using raised cosine pulse shaping with a roll-off factor of 0.05 to accommodate these channels given the channel spacing. So the modulation format initially is 32 QAM, and so this is what we are applying using the driver of the modulator. So at the output of the modulator, we have then the 8 channels being modulated. So the modulation is applied to all the 8 channels in this case. We are testing a single polarization modulation. And then here we do some adjustment to the power using this amplifier with a specific noise figure as well. And then we do the transmission. Initially, in this case, for 32 QAM, the transmission distance is 500 meters. And then at the receiver side, what we do is to filter in one of the channels, the channel of interest, and that's the monitor channel, we call it. And then we use a standard structure for the coherent receiver. So this is the coherent receiver. We can look inside. We see that this is based on this photonic circuit component, the MMI, that represents a 90 degrees hybrid. We do balance photodetection here with a specific CMRR and responsivity imbalance as well, that's specified. We do the bandwidth limitation, and at the end here, we digitize the signal using this analog to digital converter with a specific resolution. So if we go back, we can view the parameters for this coherent receiver. As you see here, so the parameters for the local oscillator, the MMI, the balance photodetectors, and the ADC. There are more parameters inside of the Galaxy that can be customized. We just chose the main parameters in this case to show on this level. So after this, we do the digital signal processing. This is the standard digital signal processing. Now, because we are transmitting in the O band, we are not doing CD compensation in this case. We just have these algorithms for IQ imbalance correction, clock phase recovery, the time domain equalization with multi-modulus algorithm, and then we end with carrier frequency recovery and carrier phase recovery. to compensate for the phase noise of the transmitter and the local oscillator. So now if we see, like looking at the system, we imagine now this system needs to be on this is for a data center application, and we need it to be on in a small factor. So we need this transmitter. The components here need to be on a photonic chip. So using then photonic integrated technology, we want to manufacture this, and the same applies to the receiver components. And here we notice some crucial components, such as the optical frequency comb generator, such as the modulator, that if we look inside, so this is built with photonic components. So if we go back, and the same applies to the 90 degrees hybrid, as I showed for the MMI. So the role of these components is crucial, and their design process is not an easy task, but it's implemented mainly by the photonic integration in photonic design engineers. So with this actually, so this is a mutual work between the system team and the photonic component team. Actually, I would like to pass the talk to Eugene to tell us more about the design process that was used for these components in particular. So Eugene, the floor is yours.
Thank you, Nebras, and I'm really excited to step in here because one thing is already different, and you probably noted that instead of pretty well established silicon photonics, we are talking about thin film lithium niobate technology, and this is a new emerging technology, and with really unique properties. But what is really important for us for data center application is that it really allows for high performance optical signal modulation and processing. So yeah, that's important, but again, there are tons of other properties. The thin film lithium niobate performs really interesting nonlinear properties, which are very important for photonics computing, for example. But here we really focus on this fast modulation, and that's obviously is important in our IQ modulator. But also, Teflon is a great integration platform, so we can implement other functions with it. And one of them is actually this 90 degrees hybrid. So it is implemented based on a multimode interference device. Absolutely key component in any coherent receiver. The MMI is a relatively simple integrated photonics component, and the idea is that we launch our usually single mode into the wide waveguide, and this wide waveguide supports multiple modes, and once they're excited by our input signal, they start propagate along the waveguide, and they start to interfere with each other. And if we cut our device at proper positions, and if we put the output waveguides there, we can obtain variable functions. So in this case, for example, we can see that it operates as 1x4 splitter, right? Or it could be 2x2 coupler or 1x2 splitter. So, all of them could be implemented. And what is importantly, they also have some specific phase relations, which is important for our 90 degrees hybrid operation. And the model, again, it's pretty important to have the physical model here. As we can see, the cross-section here, that the splitting, although it's, pretty good one, but the splitting ratio is slightly different, right? So it is important to account for this, because this kind of impairments really have a huge impact on our system level, right? And we need to maybe mitigate those effects with DSPs. Similar in our previous example, we support a set of test benches. One more thing to highlight here is the importance of so we discussed a lot that it is important to have accurate models, but at the same time, it is also important to have the ideal models. And that's why we try to implement both within one component, right? So we can see, let me show a result later, that we support both ideal and physical. So why is it important? And in the first place, because it simplifies the debugging. So let's imagine something goes wrong in your system, and you need to figure out what is responsible for this wrong behavior. And then switching on and off different effects is really crucial part, right? So we can identify, okay, maybe that's our imbalance in MMIs, or maybe that's our imbalance or CMRR in our balance photodiodes. So we need to kind of find those key components, and supporting different models is important, right? So for example, now I switch to physical, and we can compare the performance, right, between the physical and ideal model. So in the ideal, you see there's no frequency dependence. However, phase relations are supported. However, if we get the results for the physical, we already see some that our splitting ratio depends on the frequency. And yeah, and actually there is some imbalance in case of this MMI 2x2. And again, it's important because especially once we operate with multiple tones, right? So operate with multiple frequencies, and over the bandwidth, our operational bandwidth, we may see different splitting ratio, and we need to account for those. We can also check the performance of our 90 degrees hybrid here. So for this, I just use this little test bench. And you know, if you're not familiar, the idea of 90 degrees hybrid is relatively simple, right? So we have two inputs, one for local oscillator and another for our signal. And then those two are combined on different ports, output ports, but with different phase shifts. And this allows us to demodulate our I and Q components in the IQ modulator. So if I check the simulation results and I start looking on different outputs, right, for both inputs, we can see that, for example, for the first one, we got like 180 degrees difference, no phase difference for the second port, and 90 and minus 90 for the ports 3 and 4. So, you know, this shows that, yes, this model is a good candidate for working as a 90 degrees hybrid, and we can implement it in our system. So the second component, and probably most crucial one, is our IQ modulator. And as Nebras was showing, it consists of two Mach-Zehnder modulators, and those Mach-Zehnder modulators are traveling waves. So we use those MMIs to split and combine the signals, and then we have this electrode here in the ground source ground configuration, so that our RF signal is applied in the middle. You know, that's pretty typical configuration for the high-speed electrical driving. And again, for this test bench, we have several different modes of operation. But let me discuss a little bit more on this traveling wave, because that's an essential part, and that's actually what allows for high-speed modulation in this particular case. So the traveling wave actually ensures that our electrical signal and optical signal propagates along the waveguides and electrodes with a similar speed. And we can investigate this. So we have, for example, group index electrical and group index optical as parameters, right? So we can see how this velocity mismatch impacts our performance. And then we have some electrical models to actually calculate the voltage which our waveguide sees, right? Because this would depend on actual position of the modulated section, right? So supposedly we have several segments along our waveguide. And this model was developed within the Selena project. So that's a project to create a thin film lithium niobate platform for PIC design. So you can learn more about it. Yeah, but switching back to our test bench, you can see that it's kind of neat and compact. That's because we are using this very specific model, test set modulator. And this model allows for automatically generate the signal and analyze the modulator outputs. Also, we support several different analysis types here, right? So we can specify, for example, for bias, we can specify what voltages we would like to vary, right, at which optical frequency, and the same for modulation frequency analysis type. We actually show the modulation transfer function for different modes. One last thing that's similar to MMI, we support 2 electrode modes. One is more ideal, right, and one is more based on S parameters. So where actually our electrodes interact with each other. To save some time, I just did the simulation ahead of time. So now we can just visualize the results. So on the top, we can see this bias voltage, and we can use it to define the operational point. We see that the models for the static characterization are pretty much the same, right? However, if you look at the modulation response, we can see significant impact of the electrodes and their electrical properties and their impact on the bandwidth. So yeah, maybe we need to play around. Maybe we need to optimize the biasing, for example, in order to achieve a little bit higher modulation response. But once this is done, we pass the models to our optical system specialist and explore how they could be incorporated in our coherent system. So Nebras, yeah, let's show how they work.
All right, thanks, Eugene, again. So back to the system level. So let's say, as a system engineer, I receive these components from the Photonic components team, the modulator and the 90 degrees hybrid, and I want to test them in the system. And there are actually many things to test in this on the system level. For example, what's the effect of the imperfections in the modulator? How about the MMI? Can I use DSP to mitigate these imperfections? Also about the some system metrics such as the let's say the roll-off factor, the bandwidth limitation of the driving circuit to the modulator. There are many things to explore, and that's a part of the design process. But in this case, we chose some of the tests to highlight, and I'll tell you what these are. So mainly, I chose to start with the case of course, the modulation format is 32 QAM. I want to try back-to-back, and we started actually without TDE, or without time domain equalization. And we want to see, so in this case, this module is inactive, okay? And for the modulator here, now you know the differences between ideal and physical from what Eugene showed. So we chose these to be the electrode model is ideal, and the same for the MMI model here, ideal. Same for MMI here. So model type is ideal rather than physical. So that was the starting test. So that's one case. And then, you know, with 32 QAM, we have a 2 terabit per second. We'll be switching to a lower order modulation format and seeing the difference in performance. So that was case number 1. We'll be looking then at the demodulated signals here before launching into the fiber. We'll be looking at the constellation diagram for the monitor channel. That's channel number 8 in this case, last channel. We'll be looking at also the signal before or after filtering here, after this filter. And just a reminder here, we are also doing parallel detection. So all the 8 channels are processed here in parallel. So we get the SER for all the 8 channels. So that's test number 1. Then I want to try to switch this on to try to S parameters and physical here for the modulator, and the same applies for the MMI here. Switch to the physical model and look at how it performs without the TDE, just with the rest of the DSP chain being active. That's case number 2. And then I want to activate the fiber and activate the DSP and look at case number 3, see how it works with physical components here or physical models with TDE on. And lastly, I want to try to change the modulation format from 32 QAM to a lower order modulation, but with a longer distance. So now we have 500 meters and 32 QAM. That's 5 bits per symbol. But with this macro here, I run this macro, 16 QAM, and this changes the modulation format to 16 QAM and the 4 bits per symbol. And the transmission distance would be 10 kilometers. Of course, this means a lower bit rate in total. That would be 1.6 tera in that case. But I obtain a longer transmission distance and that's a typical, that's the advantage of Coherent. Like that's flexibility, the trade-off between modulation order and transmission distance, which is useful for data center interconnects applications. So let's look at the results. I have them already there just to save time. So this is case number 1. In case of back-to-back 32 QAM, TDE is off and ideal components. So this is the spectrum, the optical spectrum for the launch signal into the fiber. As you see, we have the 8 channels. We have some variations in power. That's the effect that's coming from the frequency comb. That's a known effect. Also, we have here the filtered signal. So that's channel number 8. And that's after filtering. We can copy the trace here and just paste it here and compare it. So the filter here is doing a good job. Here we have the SER versus channel index. So these are the SER for the 8 channels. We see that some of the channels perform under the FEC threshold. Of course, we need to convert from SER to BER and decide on the particular FEC that we'll be using. But in general, we can see that channel 8 has a high SER relative to other channels. That's likely not going to work with most FEC thresholds. And then here we can see the constellation diagram in this case. Just remember that TDE is off in this case. Now let's switch to the second case with physical components. So that's with ideal components. Now, this here is the case with physical components. We see that the spectrum is affected by this with these imbalances and these imperfections in the modulator. So because it affects the shape of the pulse and that impacts the spectrum. So we see that effect here, just going back and forth. These are the old results for the first results, and this is the results for the second case, as you see. We see that the channel or the performance is rather bad. So if we switch to text here, so this is the SER for the 8 channels. We see that the impact of using physical models is very significant here. And there is no good constellation that I can obtain. Now, when we try TDE on, switching TDE to on with fiber propagation, we see that TDE here, how useful it is, that it actually fixes the problem here for us, these imperfections coming from the physical models. And we obtain a pretty good constellation diagram for channel number 8. And we see the performance of SER in terms of SER versus channel index. That's also very reasonable. Okay. And lastly, for the test number 4, for the case of 16 QAM, I switched to that. And we see also, this is we can observe a good constellation diagram for channel number 8. And the SER is also very, very well for the 8 channels. So again, there are many other tests that can be performed. We just chose these tests to show and highlight. And yeah, with this, probably before moving into receiving your questions in the Q&A sessions, I'd like to pass the talk to Chris to wrap up.
Yeah, thanks, Nabras, and thanks, Eugene. So just to summarize our story today, a few things, right? As data rates increase, PIC-based optical interconnects continue to replace copper links in the data center. But design complexity arises from challenges in designing those PICs for optimal system performance. So therefore, the PICs can be tuned and optimized for full system level performance in a seamless workflow using VPI Photonics Design Suite. So yeah, feel free to reach out if you have some interest. We can provide a demo or a free software evaluation. Our email, you can email me directly. You see the contact information there.